So motivated by this, we tried a different propagator, and that was more in line with quantum field theory. And this was defined to be the vacuum expectation value of two field operators. And this has the interpretation that, this is the amplitude of a particle being created at some space-time point y, and then it propagating to another space-time point x, and then getting absorbed there, or vice versa. So, in the previous lecture, we evaluated what this function was, and it's very easy to evaluate. And we found that the function was given by something like this. Now we want to look at the asymptotic form of this dx minus y, but for time-like and space-like separations. So let's start with time-like separations. So for time-like separations, we can always go to a reference frame in which x, the three-dimensional vector x, is equal to the three-dimensional vector y. And if I do that, then my function, my propagator, becomes, if I write this now explicitly, so this is k Now, this is a three-dimensional integral. So what we can do is that we can go to the polar coordinate. And if you go to the polar coordinate, it becomes, we can do the angular integrals, which give me 4 pi. So I'm switching to k to p. And then if I make a change of variable from p to so p here is the modulus of the 3 vector p. And if I make a transformation to energy, then the integral becomes an integral from m to infinity. And then I have an integrand which is e squared minus m squared e to the power minus I e of t d of e. Now again, we don't have to do this integral explicitly. What we can observe is that we are interested in the first case for time-like separation. So we want to take the limit where t goes to plus infinity. Now here we see that when t is large, this is going to oscillate very rapidly. So the major contribution to this integral will come from the lower end of this value of e, which has the value of m. Therefore, the asymptotic limit of this integral will be in the limit where t goes to infinity. This will be given by e to the power minus I mt. So which we see is oscillatory, which is of course something we expected because our separation is time-like. So we want signal to propagate like in waves. Now, if I take for space-like separation, we see that we can take our time coordinate to be equal, and then we can take x, the three-dimensional x minus three-dimensional y, to be r. Then our propagator becomes d cubed p by 2 pi cubed 2 of EP, e to the power minus I, three-dimensional p dot three-dimensional r. And then if you go over to polar coordinates, this becomes the minus I, so I leave that as an exercise. And r is the modulus of the vector, 3 vector r. And then I've done the angular integral, so we have an integral over p, and then we have p times e to the power IPR divided by square root of p squared plus m squared. If you look at this integral, we see that the integrand has a branch cut. So if I look at the p integral now, the p plane, so this is our p plane. What we see here is that from the value of p given by plus im and minus im, we get a branch cut. And we can take the branch cut to go to the infinity in that direction. And this is because we have a square root here. And our integral, our contour is going along this direction. Now what we can do is that we can say that we can look at the following contour integral. So if I'd taken this p plane, and then I have this branch cut structure, and suppose I did a contour integral where the integrand was the same as here, but now the contour went like this for a large contour, and it closed like this, and then of course it came back and it closed like this. If this was the contour and this radius was r, in the limit where r went to infinity, what would happen is that the contribution to this integral from this part of the contour and this part of the contour would be vanishing because of this exponential factor. And if that is so, then the integral over this part of the contour plus the integral over this part of the contour would add up to what the residues are of the singularities inside here. But there are no singularities here, so the residue here is 0. In other words, the integral over this, the real line, and the integral over this bit would add up to 0. And therefore, we can do is that we can say that we can then take this thing, and then because using the path independence, we can deform it to be an integral over the contour, which goes like this. So we can deform it continuously to this thing, to this contour, and this would not change the value of the integral. So if I do this, then I can write the integral over there in the following form. I can introduce a new variable where rho is equal to minus I of p, and a little bit of manipulation shows that then our integral becomes 1 over 4 pi squared of r, and the integral from, what is this point? This point is I times m. So here in the rho variable, it becomes m, the lower limit, and this becomes infinity. Then we have a d rho, then rho e to the power minus rho of r divided by rho squared minus m squared. This is my integral. I mean, these, to get to this guy from over here, it's just a mechanical manipulation using this and this picture. And this picture. So I leave that up to you as an exercise. But if I look at this integral now, we see that we are interested in this integral for large values of r. For large values of r, we see that this is going to be where it's going to suppress the integral. So the major contribution to this integral will come from the lower limit of this, which is the value of rho at there is m. So what we can say is that, roughly speaking, the propagator in the limit where r goes to infinity, the r dependence will be given up to some factor by minus mr, which is decay, but it is not zero. Thus, we see that our attempt at generalizing the non-relativistic or the relativistic propagator to a quantum field theoretic propagator still doesn't work.